This should work here. Should be live. Can you guys tell if it's going yet?
I'm not on the YouTube side.
Okay, I have it up.
It says meeting is now live streaming on YouTube. So
Question is it on the correct link? Hold on a second here. Oh, this is so frustrating.
Technology is just not as
because this happened last time when I tried to go.
I'm gonna go to
select the date and time. Yeah, no, I want to go live now. Why isn't it doing it?
just waiting for Ellie in space on the YouTube right now.
Yeah, what the heck? Okay, wait, hold on. Oh, it says it's being live streamed.
yeah, that's what I see.
Oh, it's working. Oh, it's working. Okay, live. We're good. We're good. Okay, sorry guys. We are live, so make sure to be on your best behavior. But Jonathan and Jeff, this is your first time meeting, so yeah. How are you guys doing? We're all in different parts of the country right now.
That's right. I'm out here in Somerville, Massachusetts, just a mile or so from Harvard. And yeah, it's been a lovely day for a change here in Massachusetts.
It was snowing here in Salt Lake City most of the day. So what's the weather like there in Boston?
No, it was sunny and warm today. We've had our share of snow this winter, but I actually went for a walk. It was very pleasant.
Which means you're feeling better, which we all love to hear because we need you, Jonathan.
Yeah. No, I just was sick for a couple of days, but
Oh no.
And so of course, because it had some of the symptoms, I was like, oh no, I've got COVID, I'm gonna die. But in fact, it was just a stomach bug, and I felt pretty miserable for a day or two. But now back to my normal level of old and decrepit. So that's okay.
And then Jeff, you're in California, so maybe tell people a little bit about that.
Oh yeah, I'm in LA, which we always have beautiful weather. So today was another beautiful weather day, of course. So it was nice. We actually got a little bit of rain last night. I was really surprised. So
okay.
But just a little bit, it's just to clean up the air and get rid of some of that smog. But yeah, today's been a nice day. So, and I still got my my evening left ahead of me. So
yes, and let's get right into talking about James Webb Space Telescope and kind of the exciting updates. It's making headlines again. So tell us, it sounds like you're pretty pleased with the sun shield that's maybe doing better than you thought.
It's doing a lot better than we thought. Yeah, I mean, NASA just released a press release on Wednesday about some of the first, actually the first color image that they sent out, because they're still in the alignment phase, of all the instruments and the mirror and everything. So right now we're seeing these test images. They're not the actual science images yet, but for being a test image, wow. I mean, I was so amazed on Wednesday at this new color photo of this star that they're looking at to align the near cam instrument, and then the selfie that they put out of all 18 hexagons on the mirrors. Just so cool to see. And that's a big reason for all those pictures coming out so well right now is the sun shield and how well it is actually working to cool everything down passively, because that's what we're seeing here. The way the telescope gets cold the way it is now, it's because of that sun shield blocking out all the sunlight and earth and moonlight, everything coming towards the telescope. So that's why we can see this beautiful red radiant star. And then what's even cooler is all the galaxies you see in the background. How cool. I mean, I did not expect that for looking at the first star. I thought it'd see just kind of black because it's not a very long-term image. It's not staring at it for hundreds of hours like it's going to do when it does its science. So just seeing all those galaxies already, I mean, I can't wait for these real science.
Yeah, that all the astronomers I've been talking with, that was the bit that caught our attention, especially those of us who are old enough to remember the first HST images. And you know, it's one thing to get a sharp central core to your PSF, but having those galaxies in the background means that the sensitivity to extended sources is there, which means that the thing is properly in focus, not just in the core, and that the background isn't horribly high, and things like that. And so there's actually a lot of information in that image about things that could have gone wrong but didn't. Yeah. and so that was for the first time I'm really starting to breathe a sigh of relief there, seeing that data.
Yeah, I mean, to see that the optics are working and we're getting an actual picture, I mean, that was a huge sigh of relief for everyone, right? I mean,
right. Not just the optics, but the detectors and
the detectors. Yeah, there's no obvious like contamination or anything. There's nothing blocking those light paths. So I mean, it's amazing. It's such a good sigh of relief for sure.
Yeah, and just for context, you know, there's even very successful missions often have, you know, some issue. Like, for example, one of the most successful astronomy missions in recent years has been Gaia, the astrometry satellite. But it had a little piece of insulation peeking over the edge of the camera that was reflecting light that made it unable to see the very faintest stars it was designed to see, right? And that's, you know, just these very subtle things that can, you know, not destroy the mission, but you know, compromise the ultimate science that you want to do. And it was still able to work around that, but you know, and so far, you know, there's nothing like that. And when you build such a complicated spacecraft, right, with all these fragile parts, and then you put it on an effing big rocket and shake it on the way up into space, it's, you know, you got to be prepared for something to have fallen off, right? And so
yeah, or to move around or to get jostled, you know, and not be in the right spot where you want it to be. I mean, that's what we test for, right? That's what we make sure.
Exactly. But there's, you know, it's not uncommon, even in the really successful missions, what I'm saying, for some minor thing to have, you know, to have gone wrong. And so far, as far as I can tell on JW, that, you know, it's sort of perfect down the road so far. So, so that's very exciting.
There were so many major things, right, that could have gone wrong with this thing, but you're right. It's the minor things that you know, like, oh, it's just a bit of thermal insulation. We'll just put it here. It's going to be fine. No big deal. But like you said, on that other one, you know, it kind of peaked up, peeled away.
And that's the thing, because we had, you know, we put like the smartest people like you on the obvious hard thing, right? The sunshade. And you know, sounds from what you're saying that we could have, you know, launched 5 years ago with a crappier sunshade and we'd have been fine. You killed it, right? But it's not just these, you know, 10, you know, dozen or so super hard, challenging things. It's the fact that there's 10,000 totally trivial things that you've all got to get right.
You are exactly
that don't all get the same level of intention, and it just takes one, you know, to do that. And so
that's right. Yeah. That's right.
Dan asks, how does James Webb Space Telescope change its focal point? Anyone know?
Well, I mean, the telescope itself, we, you know, focal point, I'm not sure about that, but you know, the telescope.
I think it probably just means the direction, the thing it's looking at, right?
Yeah, I mean, we have, you know.
The whole spacecraft turns. Is basically,
the whole spacecraft can move. We have reaction control wheels on board. We have small thrusters, so we can move and, you know, point ourselves to a specific area and just stare at that spot. You know, and then,
now there is, I mean, the primary mirror, right, is
it's fixed.
It's fixed. So it's not like a ground-based telescope. In a ground-based telescope, it moves in two axes, right? It can turn around and it can pitch up and down, and that's how you turn it to point at a particular point in the sky. But JW isn't like that. The whole darn spacecraft turns around if it's going to look at something new. And that's why your sun shield is so big, because it has to still shade you even when you're like 60 degrees off the midnight direction.
That's right.
Let's see. Bugatti 1966 says, why was the James Webb Space Telescope launched from outside of the United States?
So we had an agreement with European Space Agency, I think over 20 some years ago, that they were going to be a part of the program. They built an instrument for us. They're also, going to do have some time on the telescope as well. And so, there was a collaboration with NASA to be able to launch on their Ariane 5 rocket. It was also at the time, back then when that was the best rocket for us at the time that we could really fit on and get to where we wanted to. And launching from French Guiana right near the equator, we get a really good boost to the L2 position too. So we're pretty heavy telescope. I mean, we saved a lot of mass compared to Hubble, but still, it's still a pretty big, massive telescope. And so anything extra we could use helped us as well. So it was all around benefit to utilize European Space Agency and the success path of the Ariane 5 and the capabilities that they had to get us to where we needed to go. And because of them and how they launched us, we almost doubled our life, I think, expectancy for Webb. We were supposed to be a 10-year mission, because of fuel reserves, and now because Ariane did so well in getting Webb to where it needed to go, they're expecting 20 years of life, based off the fuel that we've got left on the spacecraft. So it's a very good thing that we did that.
Yeah, I mean, I get, there are two levels of answer, right? One is, why use a European rocket? Because it's a European telescope as well as an American telescope. My European astronomer friends get very annoyed when it's described as an American telescope. It's a American, European, Canadian telescope. And the second order reason is, one of Europe's big contributions is we'll give you the rocket for free, and so as part of the deal. And so pay Elon X $1 million. I mean, it didn't exist back then, but buy a Falcon 9 for X $1 million versus free Ariane 5. Well, okay, let's take the Ariane 5. So now the accurate assertion is great, and we're in the L2. One thing I've been wondering about, Jeff, and maybe you can tell me, is the pre-launch suggestion was that we'd be doing the first station keeping burn like by a few weeks ago even. Do you know if we've done the first station keeping burn yet in L2?
I don't. I know it's like every 21 days they do a burn to kind of keep it.
Right, and so it's some number like that, and it shows, so there should have been one by now, and they haven't said anything, and I assumed it just happened and they decided it was too boring for the world to know about.
That might have been it.
But I want to know.
I know. A lot of people want to know. Yeah, unfortunately I don't have any of that information.
That's fair enough.
Not boring for Jonathan.
I know.
And I just realized you guys have both been to French Guiana. So
awesome.
That's so cool.
Well, this is my first trip in December, so
I went back in '98.
Oh, okay.
I saw an Ariane 4 launch. I basically was doing a project to locate. This was before Google Earth. I was locating the latitudes and longitudes of all the launch pads, and so I wrote to my friend at Arianespace going, I want to know exactly where the different Ariane launch pads are. Do you happen to have, GPS values for them? And he said, no, but we've got a plane going down there. Do you want to come along for our launch next week? And I went, let me think about that for a nanosecond. And so I got a junket. It's the only junket I've ever had in my 40 years of writing about space, but I got a junket down to see an Ariane launch. It was fabulous. And I don't know what your experience was at Kourou. So you land at KN, right, of Pepper fame.
That's right.
And then you get bussed out to Kourou, and the first thing I noticed was that as you go into Kourou, I don't know if you know France well, but the kind of town sign is like the same font as a French town sign, and the first building beyond the town sign is the Renault dealership, and then there's, you see all these French type shops, and then you get to the space base, and it's guarded by the French Foreign Legion, the Légion étrangère, and
it's all those guys for sure. Yeah, they were all, especially when we were rolling out the vehicle and everything, they're
pretty serious.
Oh yeah, very serious. Yep.
Yeah. And they have they put you out. Did you get to stay at the Hotel de Roche, the hotel that was?
No, I stayed at a hotel called the Atlantic.
Okay. Well, it may have been renamed by now.
Maybe it was right near the launch base. It was right near the launch base. So
yeah, this one was a little in the Kourou. That was pretty close to the launch base, I guess, but halfway between there and the Kourou town, and it was on the site of the old prison. Where if you've seen the old Steve McQueen movie Papillon, where they used to, French Guiana used to be like the prison colony,
like the Devil's Island area, right?
Devil's Island is right off the coast, and that's where the tracking station is.
Right.
And so there, there's all of this history around it, and so this is a very nice hotel, and they have some wonderful buffet with like Caribbean French food, and
the food was great.
I've got to tell you, having been there to French Guiana and having been to the Satellite Motel in Cocoa Beach, I'm sorry, it's Ariane every time for me.
It's funny.
Oh yeah, I have to agree.
We have a couple more questions about James Webb Space Telescope. So Dan, I guess what he meant by focal point is how do you zoom with? So can one of you guys explain that?
So this mirror, right, has all of these actuators on the back that can tilt the mirror segments individually, and so that's how you sort of align the reflection, and they can go in and out a little bit, and so you get into focus. So there's a fixed focus, but you don't have a zoom like on your phone or something like that. It's really just a question of you're always at the maximum zoom, I guess, is one way to think about it. Is that fair, Jeff?
Oh no, Jeff.
Oh, Jeff is frozen now.
Oh no, what do we do?
We trust that Jeff will reappear. Maybe we talk about eggs or something. No.
Oh my gosh. Okay, let's see if there's any questions you can answer. Oh no, well hopefully he'll come back.
That's good. That's a good sign. That means he's coming back in a minute.
Oh, there he is.
Yeah.
Sorry guys, this is live, so of course there you are.
Hey Jeff, welcome back.
My internet is going frizzy on me, so
it's all right, we got you back. Okay, so
we were talking about zoom, and I'm saying it's basically always at the maximum zoom. Is that a fair statement?
Yeah,
I think so. Yeah, I mean, I know you're talking about the mechanisms and stuff, and they use that to basically do these alignment tests that they're doing right now. So
there isn't a way of going like, oh, we're going to zoom 2 times in, 2 times out. It's always at the same, has the same field of view, the same magnification every time. And we lost Jeff again.
I know.
I don't know if that's going to keep doing that, so I apologize. I don't know what's going on with the internet there, but
we'll just
right,
make fun of you when you're not here. Yeah.
What you're saying is correct. Yeah.
Yeah. So what else we got?
So Michael Maxey wants to know, have all of the cameras been calibrated?
No, yeah, the one that they've done right now is just the near cam right now. So that's the main one they start to do the alignment process with. That's the one that is calibrated right now. It's got, first they kind of start out, they've got to line all the primary segments. So they got to take a shot of they look at that star, but all the 18 segments aren't really lined up yet. So they got to look at all those points, and then they put them in the orientation where the segments are. They focus them in, and then they stack them on top of each other to make one, single picture. And that's all done with the near cam. And they keep focusing that, and that's where we got that new image of the star on Wednesday. And now the next phase, what they're doing is they're going to go across the other 3 instruments and align them using mathematical algorithms and getting the telescope basically well balanced between all 4 instruments, the primary mirror segments and the secondary mirror.
But that's just the astrometric calibration, where it's pointing and so on. There's also sensitivity calibration, color calibration, all of these different aspects of being able to, because when we take an astronomical picture, we don't just make a pretty picture, right? We're able to measure like how many watts per square meter was in each pixel and things like that. And so that's all. I mean, of course, a lot of that, I mean, they spent years, right, calibrating these cameras on the ground, but now they're back in space. In space, you've got to calibrate them all over again in space because you don't know what's happened to them. And so there are different kinds of calibrations that are done in this process of commissioning over the next couple of months. And then there will be calibration data taken, you know, probably every month for the duration of the mission, as you try and characterize how the cameras change with time, right? For example, you can get tiny amounts of contamination on the camera surfaces and things like that. And so you've got to keep measuring what the performance of the different instruments is in, you know, in positional accuracy, in sensitivity, in color calibration, in all of these different aspects for all of the modes of all of the instruments. And so there's a calibration group in Baltimore that's got, you know, they got full-time jobs for the rest of the mission to just keeping that going.
Yeah, this kind of is a similar question, but Fedora wants to know, what are the next steps for the James Webb Space Telescope before it becomes fully operational? Do we know when the first, or what the first observation will be?
They haven't told us what the first observation will be. They're kind of keeping that to themselves right now. But as far as the next phases, yeah, we've got about, you know, another 6 weeks of calibrating those other 3 instruments, getting those balanced and making sure they're, you know, the mirrors are in line with them, going through those mathematical algorithms and computations. About 6 weeks of that, and then they take about another 6 weeks, I think, to also, you know, take out any kind of minor errors that they're seeing. They're expecting end of June, beginning of July to actually start doing the science data.
Yeah, and there's also, I mean, one of the big steps that still we're still waiting for, I believe, is the MIRI cryocooler full cooling, right? That's still cooling down. So they have these 4 cameras, and 3 of them are at was it 40 degrees above absolute zero? That the wonderful sunshade provides. And then MIRI, because it's further in the infrared, needs to be yet colder. And so it has an active cooler. And that's still chugging away, the refrigerator cycling, trying to get it down to 7 degrees above absolute zero. And then there's all these other calibrations to do. And then they begin what's called cycle 1. And there's an annual cycle of science observations. And the first part of cycle 1 is what we call ERO, early release observations. And so they have a pool of targets that they've announced they're going to look at in these early release observations. And they're going to be released to the community over the summer for astronomers to kind of check out James Webb data, so that to help them plan their cycle 2 proposals to know what the data really looks like. And so these early release observations have been picked as like characteristic of the sort of things that JWST is going to do. And they include galaxies and exoplanets and star formation regions and quasars. And so we have that list, but we don't know what order they're going to be done in. And that's probably going to depend on exactly when they start getting ready to do it. That they only make what we call the short-term schedule a couple weeks in advance, when they go, okay, here's our pool of things we want to look at. Where are we in the orbit right now? What day is it? What's the most efficient order to observe them in? You know, so that I don't go, for example, so that I get to the one, I observe the one that's like most at midnight in the darkest part of the sky, and then the next one I observe, I don't have to like move the telescope over here and then move it back over there for the one after that, right? And so there's a lot of optimizing that gets done, and so that's why there isn't a fixed, this is the first one we're going to look at.
Okay. Paul Urban wants to know, why is MIRI cooling down so slowly?
Well, I don't know if it's a slow thing. It's, you know, the first step in getting the instruments aligned was to use the near cam to be able to basically actually to get the primary mirror segments all aligned so they're all focusing on an object, and the light path is correct from the mirror to the secondary mirror and then into the instruments. So that's what the team was focusing on mainly over the last month and a half or so, was that near cam calibration. And then the next just logical step, next step what they can do is starting the other instruments. So, we don't want to waste time, cooling it down. We don't have to get there yet. We want to start cooling it down when the time is right. So that process is starting very soon. And so then it just takes a little bit of time to get that refrigerant, the coolant down to the right temperature and get it up to the mirror. I mean, that's one of the cool engineering things about the cryocooler we got on Webb is it's unique because it has to cool over like a 10-meter length, whereas most cryocoolers are only going over like centimeters. So the engineering, complexity of this cryocooler is just amazing. That it's got because the cryocooler itself is down in the spacecraft bus, which is down below the sun shield, and then it's got to run all the helium up through lines up into the telescope instruments itself to be able to cool down the mirror. So all that happening is also going to take a little while, but it is happening on schedule and in the timing that they need to do to work the calibration of everything.
I mean, I'd like to ask the questioner, how long does it take you normally to get down to 7 degrees above absolute zero? I mean, it's right. What's your expectation?
Right.
I think it's fine, to take a little while, but yeah. But I hadn't appreciated that about the spatial extent of the cooling, Jeff. That's very interesting. That does add a different time constant to the cooling. Yeah.
And Glenn Hunt wants to know, once everything reaches their respective operating temperatures, will they still be actively cooled or will it be passive from then on?
The cryocooler is always running. It's always going active cooling. So it's always running the helium through the system. It's a closed system, which is great because we don't lose any of that helium gas. It's always just circulating in there. So we don't lose the refrigerant, which is good. We're limited basically on any kind of pumps that are in there or electronics, but no, it'll always be actively cooling the mirror, and then of course the sun shield will always be passively cooling the rest of the telescope and the other instruments.
And you have instrumentation throughout the sun shield, right, telling you how the sun shield is doing. Is that my understanding?
There's not really instrumentation in the sun shield, but there are temp sensors all over the telescope portion itself.
Oh, more than okay.
And the spacecraft bus itself. So we always know temperatures above and below the sun shield itself.
So you have a gross understanding of what's happening to the sun shield, but if there's something goes wonky, you don't have a way of saying, oh, it's layer 3 or it's over on that side, or
right. We wouldn't be able to pinpoint exactly which layer. There's no instrumentation in the layers themselves, but definitely temperature sensors, on the instruments and inside the telescope that would let us know.
But you also have tension sensors at the end, do you, or is that
no? There's not really any tension sensors either. We're holding tension by springs that are constant force springs that we know what that force is, and we know that they've deployed and tensioned up. So there's not going to be a way to tell too physically if we lose right,
if you have a rip or something due to an impact.
Yeah, right. You'll just know it by temperature sensors and performance of the instruments.
Yeah. Okay. Interesting. I mean, fair enough. But yeah. I had sort of imagined that there was more.
It'd always be cool to put more in, but then it'd be 5 years later we'd be launching this thing. So.
Yeah. Right. Exactly. No, we waited long enough for this guy. Yeah.
Made sure it was right.
Yeah, Gary Brasher wants to know, how are the customers of JWST prioritized? First come, first serve, or is the calendar blanked out for certain researchers? Is there a commercial return?
There's no commercial return. The way it works is that every year there is a competition, basically. Astronomers send in their research proposals. I want to look at this with this camera configuration because the science it will tell us is exciting for this reason. And then a jury of astronomers meets to review those proposals and picks the ones that they think will have the best science return. So it's not about who you are. It's not about whether you're American or European or whatever, or you know, it's about which observations will give the best science. And then if then we do get to a bit of money, because if you're an American observer and you get awarded time, you got a good proposal, we're going to give you, you know, a day on Webb, right? Then you get a grant to help you hire the postdoc or the grad student who's going to do the research. And it's not enough money, but it's something. And so there is a little bit of the budget of Webb goes to operating it, but also to fund the scientists to make sure they are able to do the science, because there's no point in taking the pictures if there's no one, you know, if the person who's trying to actually analyze the data doesn't have any salary. So, but basically it's all about the science. And at the moment, the rule is usually that then you get that data for a year and you analyze it and publish the science results. And then the data goes into the public archive and anyone in the world can download it and make new discoveries from it for free. And there's a move at the moment in NASA to say maybe we don't even have the 1 year period, maybe we just make it free immediately. And that's kind of a bit controversial, because then, you know, what's the incentive for you to put in all the effort in crafting the proposal in the first place if someone's just going to scoop you? And so there's kind of, you know, a balance to be made here. But basically the you know, this is not a for-profit mission in a financial sense. It's for knowledge profit, right? Right. And so it's let's understand the universe the best we can. Let's compete to have the best ideas that will make the best use, and the things that only James Webb can do and you can't do with any of the other satellites, right? That's the criterion.
Interesting. Crypto Man 5000 wants to know, is there a plan to fast track a second Webb since the final design and iterations known, and that part doesn't make sense? Could we make a second one in under 5 years?
Ooh.
I know there's
no make a second Webb, but Jeff, how long would it take you to make a new sun shield?
I know there's no plan to do that. You know, we built sun shields I think we built these 5 in about 3 years. We developed the technology, we did testing. We actually built 5 layers of the sun shield before the flight ones that we have actually at our Northrop facility now. Full
Could
flight
you fly
lights.
those?
You know, no, I don't. You couldn't fly them. There's you know, we did a lot of testing of them. You'd have to probably do a lot of repairs. I mean, I wouldn't say no, like they are flight material. They're the flight Kapton. They're coated in the vapor deposit aluminum. The only thing is layer 1 and 2 on our flight article, the bottom 2 layers are coated with silicon. And the template ones that we built, they have the vapor deposit aluminum. So you wouldn't get the best performance out of these layers. So it wouldn't be impossible, but you'd have to do a lot of repairs and some further testing, I think. But you could build another set of sun shields in about, I would say, 3 years or so, maybe 2.5, you know, because we got the process down. But, you know, all the other stuff, I mean, the telescope, there was no, I think there was maybe 1 or 2 spare mirrors made of the hexagonal segments, but, and all the instruments and everything. I mean, I wouldn't see it happening under 5 years.
Yeah, probably a lot of the earlier pieces, the flight pieces that were made, the tooling isn't there anymore. They've thrown it away.
And it's just, the tooling, right? The tooling all gets, you know, people don't want to store all the stuff that they built all this stuff with. So unfortunately, one-time things, tooling ends up going away. You have to probably rebuild tooling, and then you have to test everything. All the testing that we did for everything, you can't just say, "Oh, we tested this one and we're good to go." You know, you've got to test for workmanship and all that. So. I mean, you're probably talking, you know, 10, 15 years again for another another web.
By which time you wouldn't want to launch that design anyway, and you'd use
Yeah, I mean, there's
Starship
improvements you want to
and
do.
have a non-unfoldable one, right, and things like that. But in fact, the next mission, right, is the Nancy Roman Space Telescope. So in a sense, I mean, there is a successor to Webb in the planning. It's just a different mission. Right. And the main difference for Roman is that unlike Webb and Hubble, which were scalpels that look at a tiny piece of sky in extreme detail, Roman is going to look at a much bigger piece of sky at once. And it's sort of doing a census of galaxies to measure the large scale structure of the distribution of galaxies. And that will help us understand things like dark energy. So it's motivated by a very specific science question about just as Webb is. Webb was motivated by the question of what are the first galaxies look like and how did they form. Roman is motivated by what is dark energy and how does it change with time. And so let's measure the motions of the galaxies through the ages of the universe. And so then you design a mission that can answer that question. And beyond Roman, there's, what's the next one? I'm blanking, but there are other missions. Well, there is the
LUVOIR.
LUVOIR/HABEX that the decadal survey said we should merge them and do one mega one. But who knows if that'll really happen? That's still a bit out there at the moment. But so we are looking 10, 20 years ahead for future missions. And there are a lot of smaller missions. There's a European mission called Euclid that was gonna go early next year, I think, except it was gonna go on a Russian Soyuz, and that's screwed now. So it's got to find a new rocket to fly on, which will require a redesign, which might be as much as a 5-year delay. And so things are a bit messed up right now in a lot of the space industry because of the Ukraine war. So which is we could do a whole program on that, but
we could maybe we'll chat on that a little later. I thank you for a very generous super chat here from Bimmergeezer. He wants to know, will the James Webb Space Telescope study the Hubble deep field at some point?
I would bet yes. There are a number of patches of sky that astronomers have picked to be super boring, to not have anything in them that we already knew about, totally empty. And then we looked at them with Hubble, stared a really long time, and found the really faint, distant things that we hadn't been able to see before. And Hubble Ultra Deep Field is one of them. There's the Chandra Deep Field South. There's another one. There's the Boöte Survey Field. There's like a dozen of these that have had all the telescopes look at this one field, and all the satellites and all the ground-based telescopes stare at this one field and get different pieces of information about it to do this sort of deep dive on a small part of the sky. And so it makes total sense that Webb is going to do that. The first deep field it's going to do, I think, is one called CEERS, which I'm not so familiar with. But in the early release observations, they're doing a deep survey of this CEERS field. But I'm sure they'll do the deep field as well, just because it makes sense to compare the Hubble results with the Webb results.
Yeah. Anything to add to that, Jeff?
Yeah, I mean, I'm not privy to what they're going to actually be looking at, but I would assume, yes, that deep field observations are definitely probably in the books, because we're trying to gather all the light we can, being in the infrared spectrum, right? So that's what we were designed for and engineered for. So in order to do that, we've got to stare for hundreds of hours sometimes at areas, and based off of Hubble's deep field, I mean, I can't wait to see what we see. We're probably going to see no black, just all kinds of stars and galaxies, like it's designed to do and engineered to do. So I think I would say, yeah, they're probably going to do that.
And then someone earlier in the chat asked, what is the fate of Hubble? So maybe Jonathan, you can give us some context.
Right. Well, Hubble it was launched in 1990. It's still doing great. It does different science from Webb, so it's not obsolete, but it's pretty old, and they're not planning to do another servicing mission. So at some point, it's going to die, and at some point, they're going to send up some robot spacecraft and deorbit it. And they haven't got any active plans to do that right now. They've just got a commitment that they're not going to let it re-enter uncontrolled. But I would guess Hubble has at least another 5 years, most likely. But you know, the chance that it'll have another 10 years, that might be pushing it, because there's, and it's not that anything's going to run out. You know, it doesn't have fuel that's going to run out or anything. It's just that eventually something will break. That and eventually enough things will break that there's no backup, and you'll have to stop doing science with it. But you know, for right now, it's going great guns.
Hey, it's only 2 years older than me, so it's not that old. Paul Whitmer wants to know, would a micrometeorite impact completely end the James Webb Space Telescope? That's a doomsday question.
Jeff, do you want to take that? I think Jeff's frozen again, so I'll say.
Oh no.
No is the answer. It depends. A micrometeorite impact won't be a problem, even if it hits the primary mirror. At worst, it'll it'll be a gentle degradation of the data. Hi, Jeff, you're back. So,
hey, sorry.
Yeah, do you want to comment on that? I mean, I'm sure a micrometeorite through the sun shield will not be a big deal, right?
Right. We've tested for that. We've engineered for that, right? We've done a lot of testing to make sure that micrometeorite hits won't degrade the sun shield. We've got 5 layers too, right? So we've got our thickest layers on the bottom there, layer 1. So it's going to deflect most of those and not be an issue. And even the mirrors were tested for micrometeorite hits. So because we have such a large mirror, which is great, a small micrometeorite hits, in certain areas won't affect the overall picture of everything. You probably wouldn't even notice it in a lot of the.
Yeah, I mean, it depends how micro, right? If it gets hit by a 10-meter asteroid, then you're out of business. but
those things will be gone after that. Yeah.
Yeah, but there's not many of those, and there's even the environment at L2 is pretty benign in that respect.
I was just going to say that. Yeah. L2, nothing out there, right? So.
Yeah, I mean, there's no worry. One of the nice things is, compared to Hubble, there's no worry about artificial space debris out at L2, right? Which for a telescope like Hubble in low Earth orbit, yeah, you worry a bit about micrometeoroids, but you mostly worry about artificial orbital debris. There's much more of that. Out at L2, that's not the case. You're dominated by the micrometeorites, and there's just not that many of them. And so I'm really not worried for the duration of the Webb mission. It's not a big concern.
Yeah, I'd agree with that.
That's good. I want to say quickly, thank you for the super chats from Planet Loco and St. Miles. Thank you guys for interacting right now. Canon Lucas wants to know, can the James Webb Space Telescope take a picture of Oumuamua? Jonathan laughs.
I don't know how bright Oumuamua is at the moment in the infrared. I mean, it's on its way out of the solar system. It's not that far out. It's probably like, I don't remember, but it's maybe out as far as Saturn now or something. But it's pretty damn small. And so, I don't know the answer to that. You'd have to put in a proposal, calculate how long a Webb observation you would need to detect it, and then make some science justification for why it would actually be helpful to see Oumuamua in the infrared. It's not clear to me that it would. So compete with everyone else for the observing time.
My cats get like progressively crazier as my live streams go on, so they're being nuts. So if you see me looking down, that's why.
I saw it try to photobomb you a little earlier. Yeah.
Well, he's trying to get this stupid little fish, and we don't want him to jump on the keyboard. Okay, so Andy wants to know, how does JWST stay focused on one spot for hundreds of hours while it's moving around L2?
I think it goes back to the controls. We know the reaction wheels. We're able to control where it's pointing to. We're able to do small adjustments with our thrusters. So we're able to really, keep the spacecraft very stable when it's looking at its points. We have fine guidance sensors that are able to keep it pointed at what it's looking at. So it's all in the instruments and the way we control the spacecraft. It's the way it's engineered is to stay focused on certain locations and not move off of that for the hours that it needs to look at it.
Yeah, so the key thing is these fine guidance sensors, right, are like finder telescopes. They can see bright stars, and so you can use those to figure out where am I pointing right now. So you know where you're pointing right now, you know where you want to be pointing. So if you start drifting, you notice it. And then it has what we call reaction wheels. And so the reaction wheels are, you have these spinning wheels. And if you change the rate at which they spin, conservation of angular momentum means the telescope will spin the other way. And so you can use that to just use electricity to turn the telescope around and point it at a slightly different place. And so by combining your knowledge of where you're pointing with the FGS and the control over where you're pointing with the reaction wheels, you can stay staring at a particular direction in the sky as long as you like. That solving that is just engineering, says the scientists. So now that's of course not so easy, but
Glenn Hunt wants to know, is the trend of the great space telescopes to do what the predecessors have done, but over a greater range of frequencies and over greater areas of the sky?
I would say it depends. It's driven by the science, right? That each of the great space telescopes solves some major science questions, but opens some more. And so then in the decadal survey process that we just went through, you say, okay, what are the new big questions and what kind of telescope would you need to solve them? And so, yeah, the effect of that often is you're either exploring a new wavelength range, or you're exploring, I mean, for example, the difference between Webb and Hubble, right, is the idea that Hubble can do particular measurements on nearby galaxies. We want to be able to do the same measurements on more distant galaxies. So what do you need to do that? Other things are, sometimes you go, well, we need a better ability to see changes in time, to see rapid variations, like when a star explodes. And so that leads you to do a ground-based telescope like the Rubin Observatory that images the whole sky every night so that you can see if something's changed since yesterday. So it's all about what science question are you asking?
And then let's see, Handyman IRD wants to know, would the telescope be able to scan the space of flight from Earth to Mars and help the spaceship to avoid objects, asteroids that might endanger the spaceship? Your face.
What do you think, Jeff?
I don't think that would be a mission of Webb, unfortunately. Definitely, yeah. Again, we're pointed away from Earth. We don't want any of that light radiation or anything from Earth, getting into our optics. So, yeah, and I don't think that's, again, like John was saying, right? Our science missions are first galaxies, first stars, exoplanets, things far out there. I think they do plan to look at some of our own planets in our own solar system as one of its science missions, but yeah, it's more for the planetary science and the stars and galaxies and first light. So I don't think we'll be doing that one, unfortunately.
Right. Yeah, we have other telescopes that are optimized to look for orbits of asteroids.
Okay.
And so the way that you would do that, you don't support a particular mission, you just do your best job at doing air traffic control for the solar system, knowing where all the asteroids are going. And then the people who fly the Mars probe use that catalog to make sure that they're not going through anything they don't want to go through. So it's a kind of decoupled problem.
Cannon Lucas wants to know, can James Webb detect pollution of extraterrestrial civilization?
Maybe. One of the exciting things about James Webb is that, and it's a science problem, we designed it for this galaxy science problem, right? And then between that and Webb actually being built, exoplanets were discovered. We didn't know there were exoplanets and when James Webb was first thought up. But one of the things it can do is measure this, what we call the spectrum of the atmosphere of an exoplanet. And so what that is you get the light from an exoplanet, you divide it into many colors, and you get the characteristic color patterns from different elements in the exoplanet atmosphere. And so if, for example, and one of the goals is, for example, is there oxygen in the atmosphere? That might indicate a good site for life. But if you see a lot of sulfur dioxide in the atmosphere, maybe there's some asshole civilization that's polluting there. I know, or maybe it's natural. So that's always going to be an issue. And what I will say is this: that it's a kind of an edge ability for Webb. It can just do it for the few cases. And I think most of that work is going to be the next generation of satellites that are specifically designed to do atmospheres of exoplanets. And Webb is going to help us design that next generation. So it can do it, but can only do it for a few, I think is where we're at.
Steve wants to know, how many exoplanets are we currently aware of? Isn't it like 4,000?
Ooh, well, let's see if I can
Am I
look
right?
at planets.org.
Oh, I hope I'm right.
Let's see. Total planets confirmed and Kepler candidates, 5,747 as of today.
Oh.
You're close. You didn't go over, so that's okay. You were under.
Well, this is maybe not the one that's currently updated. Actually, it may be out of date. So where's I know Jesse Christensen has a catalog. Is that the one that I was looking at or not? Let's see.
My cats are shedding like so bad.
Oh man.
Anyone have cats? Are your cats shedding? Because
I got 2 cats. I'm surprised they're not in here meowing and bugging me right now.
Are they shedding like crazy right now?
Not right now. They're okay. I don't know, but they're short-haired. You got long-haired cats?
They're short-haired, but that just means I need to brush him.
Right.
We'll see.
Bring out the brush.
We'll see when I do that.
Yeah. So anyway, thousands of exoplanets was the answer to the question. Yeah.
Okay. Okay.
I'm not sure that the exact current number is.
It's hard to tell sometimes on the internet. There was an interesting question here about hold on. What is the working principle of the helium refrigerator? From Rod.
One to Jeff. Yeah.
The working principle of the helium refrigerator. I don't know what you mean by working principle, I guess, but basically we're in order to get the instrument down to the temperature that it needs to be able to really see those wavelengths in the mid-infrared, longer wavelengths in the infrared, you need colder detectors to be able to see them. So really the only physical way you could get those detectors that cold is by getting them to that 7 Kelvin temperature that we need to. And the best method, engineering physical method we've got to do that is by the cryocoolor technology that we put into Webb. So that's the main principle, is to get those instruments down to that temperature that's required to be able to see what we need to see in that infrared spectrum. I think that's the way to answer that. I don't know, Jonathan, if you got anything on that or.
Yeah, I mean, that's hardware. I don't understand hardware.
Yeah.
But Jonathan, you know everything.
Yeah, you know everything.
Oh no, very far from the truth.
But the cryocooler, I mean, it is a piece of engineering, just marvel technology. Again, the way it's got to work that distance, that's a unique thing. I think we've got 3 separate stages in it, where most cryocoolers only have 2. So a lot of things were developed engineering wise just for our cryo cooler.
And when you say a stage, you mean basically there's one refrigerator inside another inside another.
Yeah, exactly. Different groups of helium gas that's being cooled down. So, yeah.
Right. I will say that, just to sort of defend my own area of research, in X-ray astronomy, we're soon going to be launching a mission called XRISM, XRISM, which is a Japanese-led mission. That has what we call an X-ray microcalorimeter, and that has a cryocooler that cools the camera to like a fraction of a Kelvin.
Wow, that's cool.
It is. and so there are even more. And the way it works, right? The reason we have to do that is because the way this camera works is it measures the energy of the photon by having the photon hit the detector, and we measure the increase in temperature of the pixel due to one photon hitting it.
Oh my God.
Wow.
Right, and it's a big ass photon. It's not one of your lame infrared photons, right? It's a chunky X-ray photon, so it has a lot of energy. But it's pretty large, and so that gives us really high energy resolution. So that's so I think that's the state of the art cryocooler technology now, is going to be on that X-ray mission. The NASA Goddard folks have been leading that effort, and we launched one already on a satellite called Hitomi, but unfortunately, after it took 2 spectra, it decided to commit suicide and spun its thrusters up so fast that the spacecraft disintegrated.
Oh, man.
So that was unfortunate, but we're trying again with XRISM, so that will be exciting. So that's all I know about cryocoolers.
I'm just curious, did you guys watch the SLS rollout?
Oh, pictures.
Yeah, I saw stills. I didn't really follow it much.
But it looked cool.
It's it's a very pretty rocket. I'm not sure it's X billion dollars worth of pretty, but
4 billion per launch. 4 billion.
Yeah, per launch.
4.1. Yeah.
Right. I'm not sure if that's including the development costs. I don't think it is. I think that's going forward now, and yeah. So you're not going to be launching many of them. And so, it's just, if Starship works, it's hard to see SLS having a big role. If Starship doesn't work, and that's still possible, then SLS will be what we've got. Yeah, so, I mean, I admire the engineers who've made this thing, got it to the point where it is. But it's not the program that I would have funded if I was, NASA administrator or something like that, right? So we'll see. We'll see.
Yeah, Mark says outdated before it even launches.
Well, yeah. I mean, I don't know. We'll again. Starship hasn't flown to orbit yet, so yes. Let's not, there's a lot of writing SLS's obituary and saying that Starship's the solution before the ink is dry, and I hope that Starship works great, and it may well, but it's such a leap forward in technology that it's premature to be confident about it, and I think Elon would agree with that.
Yeah. Let's see. Seki wants to know, have you learned anything from the Cold Atom Lab experiment on the ISS? Are you familiar?
I'm aware it exists. It's not my area of research. So I know I have some colleagues who work on this kind of, cooling atoms down so that they're super cold and barely move, and you can get these wonderful Bose-Einstein condensates. And so I know some of the jargon, but I don't really understand the physics. Yeah, so that's out of my area.
And then Johnny wants to know, how does the refrigerant expel heat energy if it's in space? It can't work like a condenser on Earth.
I mean, it's inherent to the cryocooler design. It's able to expel heat through the system itself. I'm not
through radiation, right?
Yeah, right. But and it's and then it's conducting the cool gas up through the lines up to the detectors of the Miri itself. But yeah, that's part of the physics of the cryo cooler. From what I understand, heat exchanges, it's able to, the way the pumps work and everything, it's able to expel the heat out and send the cool gas up to the detectors on the Miri.
Yeah, but you can't use convection and conduction like you can in an atmosphere, but you can still use radiation, right? And so infrared radiation goes out, and is it the radiator? There's the aft radiator on the back side of the instrument.
On the back side of the instrument, there's an aft radiator panel that radiates a lot of that heat away. Right. And then all kinds of radiators on the spacecraft bus as well. That's taking in all that heat to the instruments and
right. And that's good because the spacecraft bus is on like the warm side of the sun shield, right?
Right. Yep.
And
exactly.
Whereas the aft radiator is on the cold side of the sun shield, and so
right.
I worry about how do you make sure the radiation from that doesn't. I mean, I guess it's on the back side of the.
It's on the back side, and it's actually it's flipped up so that it radiates, the direction of where it's radiating is away from all the telescope and the optics, but it's on the back side. So
okay, so it's angled away, and
angled away
because it's radiation, it travels in a straight line. It doesn't like convect around. So it's okay, that makes sense.
This might be a question for Jonathan. Donald wants to know, when you get an atmospheric spectrum of a planet, does that provide any clues about the density or gravity of the planet?
Typically not. You typically, in order to interpret the spectrum, you want to already know those things. The way that you get the density and gravity of the planet is you want to measure by measuring if the planet goes in front of the star and the light dips, right? Then how much the light dips tells you how big the planet is, what fraction of the star it's blocking out. And by measuring the orbit of the planet around the star, you have information about the mass. And so that together can give you the density. And so you use clues like that to get the density, and then you use that to help you interpret the atmosphere, which, the physics of the atmosphere depends on how much gravity there is and so on. So you might be able to measure the density of the atmosphere itself, but not the density of the planet.
William wants to know, he's curious why put all of our eggs in one basket with James Webb Space Telescope, considering that building 2 isn't substantially more, what is going on? Is it substantially more expensive than building just one?
I have to censor myself here.
Okay, so who wants to tackle that one first?
I don't know, Jonathan, you want to start on that one?
Well, no, I will tell you, now it's up, I'm happy, but I've been saying for 30 years that we shouldn't be putting so many of our eggs in this one basket, no offense. I have been concerned about that, and it would have been really bad if it hadn't worked. So I have been an advocate of more smaller missions and fewer big flagships. Right. Now, the counter argument is that the very best science allegedly gets done by the very biggest missions, and that is, I think that is arguable, but that's the decision that the community has made. That the way we select missions is that we have this decadal survey process, right? And you don't compete portfolios until recently, you compete missions. And so you pick the mission that's going to do the best science, and that's always going to be the one biggest, most expensive one, right? And so that's how we've sort of driven in this direction. But I think you have to have a balance, because there's a lot of great science come out of cheaper, smaller missions as well, and you need to make sure that you don't use the whole budget for the real big, expensive ones. I think everyone would agree on that. So it's a question of balance. Jeff?
Yeah, I can't really speak to, the way that NASA determines to use their budget. That's, but, the science was driving that they needed a large telescope, infrared telescope, this size, to be able to get the science they wanted. And from there, it drives all the requirements of, well, if we needed infrared, we needed this size, and we needed to fold up, and we needed a sun shield to be able to block out all that energy and that light. So, all those kind of build up from that single need from science. And I mean, from the engineering's perspective, our job is just to make that work, right?
Right, exactly, yeah.
To make it happen. And so, I mean, yeah, it is a risk to put that all in one basket, but I mean, we were gonna build and test and not launch this thing until it was ready, until we made sure everything was going to work. So, that's what we did. That's what Northrop did. That's what NASA made sure we did. And I'm glad it all worked out for that reason. Of course, we'd all like to see the science faster and quicker, but it's better to build these things and take the time it's gonna on the ground that needs to happen to be able to make sure it's going to work on orbit. Because like everybody knows, it's a big risk. There's a lot of eggs in this basket, and we had to make sure it was right. So I'm just glad that we were able to do the test we did, find the errors we found on the ground, fix them. A lot of engineering effort was involved with doing that, and I think we're seeing the fruits of that now. So.
Yeah, I agree. I would say, I think that, and this, I think you can't, as a Northrop Grumman person, you probably can't speak to this. I wouldn't want you to, but I think that NASA underfunded it in the early years, and that meant they had to skimp on testing in the early years, and so that is one of the reasons why it took so long. If they had given a more realistic budget up front, they might have caught some issues earlier and been able to do more testing earlier and get it launched earlier. So that's one of the things when you underfund something to start with, you're guaranteeing that it ends up being more expensive and longer in the long run, because as you say, you can't launch it until you've properly tested it and are confident it's going to work.
Right.
That was, I think, part of the issue with the early years of the program.
Yeah, I think there's a lot of good lessons learned, from each thing that we build, like from Hubble. There are a lot of lessons learned from Hubble went into Webb, even though we're a different telescope, we're looking different spectrum. A lot of, the mirror issues and just the reviews of everything and the testing that we had to make sure everything was right. That all came from Hubble. And then we'll take what we learned on James Webb and we'll, do better the next time on the next project, to take all those lessons learned, and hopefully we do come up with a way to have a great massive telescope like this, but be able to shorten that time length down to build it and launch it. So I think that's everyone's goal,
This is an interesting comment from I Am Practicing Piano. Webb's greatest discovery will be something no one expected. We don't know what we don't know. Prepare for current theories to fall.
I agree.
That's why we do the deep fields.
Yeah.
Right? You're looking at the empty bits of sky to see what's there that you haven't spotted yet.
Yeah, we can put all the science expectations up front that we want, such as the early galaxies and beginning of time and exoplanet spectra and all that. But yeah, I totally agree. The unknown, is going to be probably one of the greatest finds.
Yeah, this is kind of a difficult question, but Andy wants to know, can you speculate on what could be the thing Webb finds that we didn't expect? What are you hoping for? Maybe that's an easier way to answer it.
I was gonna say, if I knew that, I'd be in the money, right?
Right.
I'm not going to speculate from an engineering perspective, so I'll let Jonathan take that.
I think, it is constrained, right, by what kinds of observations Webb can make. And so I think, the most likely area to find something really surprising is in these high redshift galaxies, because that's really where we haven't had a good view before. And so we may find something that is inconsistent with current, galaxy formation models, right? Because there's a lot of theory, a lot of computer time being spent understanding how this all works. not tied to as much data as we'd like. And usually when that happens, it turns out that no, the universe decided to do it a different way. And so I think we're going to find some surprises about galaxy formation, I think. And maybe, you know, how did the first stars form? What kind of stars were made first? Was it big stars or little stars? And how did the chemical elements evolve? We think that, you know, you start off with just hydrogen and helium, and then the first stars make all the other elements, but, you know, exactly how that plays out may be a little different than we think.
I'm laughing because Light Yagami says, well, what if we find out that we're in a simulation then?
I don't think Webb can tell us that either way. So yeah.
We just don't know. William Rourke says, I've been on the edge of my seat for every update. Everyone involved with this project deserves a strong pat on the back. I'm patting you, Jeff. James Webb Space Telescope is a miracle, and he hopes it completes its entire mission and even more. So,
thank you to him. Thank you very much. That is a great sentiment. I think we all feel that way. You know, tens of thousands of people worked on this thing around the world. So thank you very much.
Yeah. And just on behalf of the professional astronomy community, I'd like to thank you and your team, Jeff, because it's, you know, we've all been so worried about that sunshade. And I've been
worried about it my past 14 years I've been working on it. So
we are very grateful that you did such a great job on it.
Thank you. Yeah,
crazy.
It's a big team effort. I mean, so many people, so many different, you know, subcontractors and with Northrop and NASA's leadership. I mean, yeah, a lot of team effort. So thank you. I'll pass that on to the people I still see nowadays.
What's your next project, Jeff?
I'm working on some development stuff right now, but nothing as exciting as Webb. I you know, hopefully one day we'll be able to work on something like Webb again, but yeah, nothing like this. So, you know, more engineering fun development stuff. So
have you accepted that you're not in a dream anymore? When we talked in January, yeah.
I haven't accepted it yet. It's been, I mean, I was maybe starting to accept it, and then Wednesday's news came out with the new selfie and the new picture, and I was like, oh, this is still a dream when I'm going to wake up from it. So, no, I hope I don't wake up from it. It's great. I like this path. So I like this simulation, if this is where we're at.
Right, exactly. Yeah. If we are in a simulation, it's a good one. So in this particular aspect, every other aspect of this simulation sucks right now. This aspect of it.
I was gonna say, Jonathan, I haven't talked to you since everything, you know, is going on in Ukraine. I've done a couple of videos about Starlink being used in Ukraine, and I just is there anything you want to comment on with like the Russian space program?
Well, I think, you know, here's the thing. Over the past 30 years, the Russian space industry and the European American space industries have become very intertwined. And we are now realizing that that going to have to be untangled. And that is going to cause a lot of pain to the space industry over the next few years. So let me give you a couple of examples.
Right.
The Soyuz rocket was being used by the OneWeb company to launch its communication satellite. They've got a whole bunch of satellites being held hostage basically in Baikonur. They've got to find another rocket to launch the rest of their constellation on. The Russian rocket was also being launched from Kourou, from French Guiana. The Russians have been sent home. That is probably never going to launch from French Guiana again. That is my guess. And several major spacecraft, including the Euclid Space Telescope, we're gonna fly on that. They've got to find new launch vehicles, which will take years. The ExoMars project was a joint European-Russian Mars probe that was going to launch this year. Now that's not going to happen, maybe ever. A lot of communication satellites built in the West use ion engine thrusters built by a company called Fakel in Russia. So, you know, that's a problem. The Cygnus cargo ship that goes to the space station is launched on a rocket called Antares, whose Northrop Grumman builds the Antares. And the lower stage is built in Dnipro in eastern Ukraine. using engines from a Russian company. And so they've got a couple in the US ready to go, but after that, I don't think they're going to be getting any more of those. So they're going to have to redesign that rocket, I'm guessing, and on and on. And so there's just so many ways in which we depended on Russian technology being part of our projects. And I should have mentioned the eRosita telescope, which was a fabulous European X-ray telescope that's been doing great science, but it's hosted on a Russian satellite. And so Germany, it's a German telescope. The Germans decided they had to shut it down because they weren't going to do any scientific collaboration with Russia. And so that stopped doing science, really important science, because, it's just, well, we can't be doing that with the Russians anymore. Wow. So I'm like ranting on these different things. That should give you a sense of, it's been a huge disruption to the space industry. ISS is carrying on unchanged. Mark Vande Hei is going to come down. The American astronaut is going to come down on the Soyuz in Kazakhstan shortly, and that's new Russian astronauts just arrived on the space station, and that's all carrying on unchanged so far. I don't know how long that can last.
Right.
The US wanted to extend the ISS to 2030. There were a lot of media outlets reporting that as like it was a done deal. But the Russians have not agreed to extend it to 2030. The current agreement only extends to 2024. And it's hard for me to see now how the US can argue for extending it to 2030 and continuing that collaboration with partnership with the Russians. Politically, it just doesn't seem to fly to me. So I am predicting that the ISS will not, people are going, oh, the Russians are going to do something crazy in the next couple of months. I don't think so. Rogozin, the Russian Space Agency boss, is blowhard who says all kinds of crazy things, but I think the ISS will carry on for now, but I'm guessing it will be deorbited in 2024 because I don't see how they're going to agree on extending it in the current political situation. So yeah, it has huge, the consequences, let's say the consequences to the space industry are trivial compared to the consequences for the people of Ukraine. Right. But space industry is what I know about, so that's what I'm talking about. Yeah. And it's a huge disruption to the global space industry.
Yeah, I was just kind of curious because we had emailed kind of like right when all of this started, and now that we've had several weeks to see how this is unfolding, it sounds like it's just having huge ripple effects.
Huge ripple effects all over the place. Every day there's some new thing we go, oh yeah, I forgot the Russians were involved in that. Oh, that's gone now. And yeah, it's and oh, by the way, it's going to have an even worse effect on the Russian space program, especially if we end the ISS partnership. It's a key source of income for their space program. The Russian communication satellites use European communications payloads. So what they do is all the communications bit is done by Thales Alenia or Alcatel or something, and that gets put on a Russian spacecraft bus. And that's how Russian television satellites work. Because they could build satellite buses, but they weren't really up to speed on the high-tech communication stuff, and so they've just been importing that from Europe. So that's going to wreck their communication satellite industry. That's going to be over now. And they've already, the Russian launch rate has been going down. It's just going to crater now with sanctions and with end of collaboration. So they are really shooting themselves in the foot in that respect.
Right. Well, yeah, thanks for answering that. I don't want to, get too political or anything. I know that's not what people necessarily want to listen to, but I was curious, just kind of, I know you've been tracking it really closely and watching everything unfold. So, yeah, someone commented, I was thinking Putin shooting down that satellite was a warning shot. And then someone said, what satellite was shot down?
Well, I don't like the word shot down, because when you destroy a satellite, the pieces stay in orbit, right? It's a misnomer to say shot down. But yeah, so back in November, they flight tested an anti-satellite weapon.
That's what I thought.
And it blew up an old Soviet dead satellite, and it was a test of this anti-satellite system. I don't think that has anything to do with the Ukraine conflict. I think that was just part of a development program that's been, progressing for many years, and it finally got to the stage of flight tests. But it does reflect the fact that the sort of aggressive stand of the Russian military space program that's has a number of different weapon systems that they've been introducing, and it was a particular it reflected the very different worldviews that have emerged in Russia and the West over recent years. That they thought it was still okay to generate a huge debris cloud that put the ISS at risk, among other things, and everyone else was like, seriously, in 2021 you're blowing up satellites, and they're like, yeah, why not? It's a military test. We do that all the time. It just reflects a certain attitude, and but I don't think it's a specific message per se.
Oh no, we lost Jeff again.
No, I don't know how long he can hang out. We've been going for a while, but
yeah, we can wrap it up soon. If you guys have any more questions, what do you say? We'll give it 10 more minutes.
I'm fine. So yeah, I'm happy to do it.
Yeah, has that been an issue? That was back in November. Has all that space debris from that created anything that you've noticed lately in recent months? I
mean, it's contributed to the to the number of avoidance burns that satellites have to do. Starlink's had to do a few. There's plenty of that. Some of that debris is re-entered now, but there's still plenty of it in orbit. They've cataloged over 1,500 pieces. So yeah, it's a problem. It hasn't like dramatically changed the environment, right? It's just made it that much worse.
Right. Light Yagami says we should really develop a machine or system that cleans debris from outer orbit if they're blowing stuff up out there. There is work being done to create something like that, right?
There are experiments in removing debris from orbit underway, and I think in a few years that will become an operational thing.
Right. Oh my gosh, some of these questions. What is the meaning of life? What's the meaning of life? What? 42. Okay. Sometimes these questions it's a great question, but it's like very deep philosophical, about.
We don't have time for a more in-depth answer, I don't think.
I don't know, maybe we've lost Jeff for good. Maybe he was not wanting to hear about Russia right now. I don't know.
Yeah.
Oh, he's entered the waiting room. Hold on, guys, we'll get him back here. Oh my gosh, my cat is just going nuts. Everyone say hello to Pinocchio, because he really wants to be a part of it.
Hi, Jeff.
Jeff, you're back. Jeff, we're gonna give it like 8 more minutes, and we'll end on a good note. I wanted to ask you, Jeff, if there's any questions that you wanted to ask Jonathan, because I know you said you're a big fan. So
yeah. Oh man, I wish I would have known. I would have came up with a whole bunch of questions.
Well, you can always. I mean, you and I can always Zoom if you just give me a.
Yeah.
We don't have to do it in public, but yeah.
I just want to let you know. I mean, I admire what you do, your work. I wanted to be a space scientist. That's always been my interest. Is space. I started out as a space science major. And I was really torn with going between engineering and science, and so I don't know. I like the engineering, right? And I really appreciate what it takes to do the engineering, but also the science and the studying of what's out there and the unknown, and just that field to me is just an amazing field. So I really have a lot of admiration for what you do, and I guess what what is your main interest, or what got you into the space science field and community? What drives you to be studying?
Right, and let me say, I mean, I have huge respect for the engineers because that's something I can't do, and we depend on it so critically. Yeah, for me, it was sort of a philosophical, where do we all come from? What is this universe? How to be? And then as I, read up about that as a kid, the sort of extreme physics, the grandiosity, right, of the universe, the scales, the time scales, and the beauty of the way that you start with a simple set of rules and a smooth universe, and you let it simmer for 12 billion years and it curdles into all this complexity. I just found that our ability to understand how that happens inspiring and beautiful, and I wanted to be part of that. And so I got into cosmology and black holes and all of that stuff, and math was something I was able to do, unlike other things. So I focused on math, and I went to Cambridge, and I was very lucky to fall into working in a group with some people like that I was in the same department as Stephen Hawking and Martin Rees.
That's so crazy.
That's so cool.
So I was able to sit at the feet of incredibly smart people who are really making revolutionary leaps in our understanding of the universe. And so yeah, that I've just stuck with it because it's been such an exciting ride. And I started in the 70s and 80s. Astronomy was developing, but was developing in some sense relatively slowly. And then in the 90s, it just exploded in terms of solving millennia-long philosophical questions, right? Like, the multiplicity of worlds. Are there other worlds like the Earth in the sky? Oh, yep, exoplanets around pretty much every star, solved. And how old is the universe? When I was in school, it was maybe 10 billion years, maybe 20 billion years. Nope, 13.7 plus or minus 0.1. And so that's a question that people have had from for millennia. And so the fact that we can take these questions of natural philosophy and actually quantitatively answer them, that for me is. So my old boss Martin Rees in Cambridge, right, his job title was the Plumian Professor of Astronomy and Experimental Philosophy. And the idea, because it goes back to the 1800s, right, before there was a word science, and the idea that science is experimental philosophy, that I love.
Wow, that's awesome. Yeah, thank you for that. That's so cool.
Well, you do great work, and I appreciate you always being accessible for Ellie in space as well, Jonathan. So we love hearing from you. And I've been told by many people that you explain things, in a way that everyone can understand, and you make, education really accessible. So we appreciate that.
Thank you. I do my best. And to wrap up, am I allowed to embarrass you slightly?
Yes.
Can we all please wish Ellie a very happy birthday for later
happy
this
birthday.
Okay.
Is it today? Happy birthday?
No, it's on Thursday. I was like,
happy birthday. Close enough.
You got me blushing. I was like, wait, why am I being embarrassed? Yes, I'm turning 30 years old.
I wasn't going to mention the date.
I'll say it.
Yeah. So happy 30.
Thank
you. Happy 30. It's a good decade. They're the 30s. It'll be great.
It's a very good decade. I've gone through that twice now.
Yes, I'm excited. I feel like it's a great age. Everyone says 30 is the new 20. So
yeah,
whether that's true, I don't know, but
it's
I feel
true.
great.
It's true.
I feel, I just did a rock climbing competition yesterday, and I feel, very physically fit and whatever. So
Nice.
30's not old.
No, it's totally not. Oh, it's totally not old. No, and I think it's like that. It's not the new 20 in the sense that you actually hopefully have a job and a salary and some respect that you don't have when you're 20, right? And so that's what I liked about my 30s was that people finally, when you hit 30, they start to acknowledge that maybe you're an adult now,
right?
Right, and so that feels good.
Well, I went out dancing the other night, and a bunch of people thought I was 24. So,
hey,
I'll take it.
A good thing. Yeah.
You can still totally rock that. Yeah. So that's right. It's, you still look young, and yet you have the maturity and the sort of respect when you need it. So,
and all the wisdom, right?
All the way. Oh, absolutely. Yeah.
Well, thank you to everyone for wishing me happy birthday, all these happy birthdays. Wow, that's awesome. I think March 24th, my birthday, is actually the same day that the first Falcon 1 flew, I'm pretty sure. Jonathan, can you fact check that?
I can quickly fact check
March
that. I'm embarrassed that I don't remember it off.
Might have been 2006.
It was indeed March 24th, 2006 was the very first SpaceX launch, the Falcon 1 from Ouma in Kwajalein.
Yes. Yeah. So I discovered that as I'm reading Liftoff, and I'm like, I'm meant to cover this. It's like on my birthday, like
it's in the stars.
Wild.
Let's see if we have any other interesting.
This is also the 20-year anniversary of SpaceX this month. So
that's right.
Happy birthday to SpaceX.
Maybe they'll amount to something someday.
Well, Jonathan.
Oh no, I'm kidding. They obviously have done amazingly well. Yeah.
I think pretty much everyone in this chat is very much in Musk we trust. So
yeah. No,
what do you think of the broomsticks jokes?
Yeah, here's the thing, right? I mean, Rogozin, he did the trampoline thing way back, if you remember that when they were negotiating for seats with Soyuz, American astronauts on Soyuz back in the day. He was like, you're going to have to come with the Russians to space, or else you're going to have to jump on a trampoline to get to orbit because, the shuttle's being retired, right? And so he has this long history of sarcastic remarks about the American space program that, he's a blowhard. He's a politician. He was a former deputy prime minister of Russia who got demoted to be boss of the space agency. And I mean, you and I might consider that a promotion, right? From being a politician, and he doesn't really have a lot of technical knowledge as far as I can tell. So he keeps coming out with these ridiculous statements, and he reminds me of certain American politicians that I better not name. So I wouldn't take Rogozin seriously, and I think that my sense is I do have friends in the Russian space program. I haven't talked to them lately, but I've over the years I've had a lot of really good contacts with space geeks who are my Russian counterparts, and I think they're all very embarrassed by Rogozin. He doesn't reflect what they think, even if they're supporters of the Russian foreign policy generally. They think that Rogozin's kind of I won't use the word. But
some of the stuff on Twitter is getting kind of nuts. The memes of choose your fighter with Elon and Putin. I'm sure you've seen those.
Oh yeah. I mean, it's come on.
Yeah, it's kind of.
No, great. I'm actually not in favor of settling wars by single combat between leaders. That's dumb.
Are you on Twitter, Jeff?
I'm not on Twitter. No.
Oh.
I know. I kind of stay away from Twitter a bit.
Yeah. I understand that.
Yeah.
But I find it really valuable. But yeah, there's a lot of noise on it.
Yes. You're like a Twitter celebrity now, Jonathan. So, I mean,
yeah, I've noticed an increase in the amount of, shall we say, unconstructive comments on my timeline. So we'll see. But yeah, it's I mean, I think I'd rather focus rather than on broomsticks and other insults. What are the real implications for the space industry?
Right.
And is there anything that space can do, to help the situation in Ukraine? I'm still unclear how much the Starlink terminals have actually helped
Really?
at this point. I mean, in terms, there's a couple of people who've got them working, right? Does it really, have, what's the number of people that are actually using Starlink for their internet? It seems like they actually do have other sources of internet still, so they're not actually depending on it. I mean, I don't want to knock it. It's a good effort, but I think the reporting on it has been a little vague, and I find that frustrating. And there are
internet, is Starlink internet good? Because my internet obviously sucks because it's going in and out. So maybe I need to upgrade.
Ellie is the expert.
I was gonna say someone earlier in the chat said that Jeff needs Starlink. So
I guess so. I'm going to start researching it now to see if maybe, because I need something better than what I've got.
How is your internet bad? You're like,
I don't know. It's at my house, but sometimes some days it's great, no problem. Some days it's like it cuts in and out. I don't know. I've got to get it checked.
Well, from the look of your background, you're at L2, so it's not surprising.
Right, yeah. It's actually not in my clean room, so this is just the background, unfortunately.
Yes.
So I'm just at home with my own crappy internet, so that's my bad. But
I will say this, Omar has asked this question like 7 times, so I'll just go for it. Jeff, Jonathan, what do you think of Russian hypersonic technology?
Well, let me have a rant about hypersonic.
Okay.
It's a word that is heavily misused deliberately by people. So every, suborbital missile is hypersonic, right? But they talk about, when you talk about a hypersonic weapon, what you usually mean is something that once it comes into the atmosphere, maneuvers in the atmosphere at hypersonic speeds, right? As opposed to an ICBM, which travels through the atmosphere hypersonically, but doesn't steer for the most part. And so, the Iskander is hypersonic, sure, but it's not maneuvering hypersonic. So it's not this high technology hypersonic that the US is currently trying to develop. And so the Kinjal that they've been using seems to be basically just an air-launched Iskander. It's no big technology advance. I mean, I sure don't want one hitting my house, right? But it's a regular conventional ballistic missile. It's not something to freak out about in terms of being advanced technology.
And I'm gonna have to stay away from that question. So
yeah,
you can comment on that one.
One of the nice things about not having a security clearance is that I can say some things.
True. That is a good point. Well, is there anything else that you guys wanted to say before we hit the high road? And
I just want to let you know, I'm very excited. You're seeing me. We were talking about being in our homes. As you can see, I'm still in my home office. But next week, I'm going to get back in my own office at the Harvard Observatory.
Really?
So, yeah. So that's both stressful and exciting.
So that means next time I come to visit, I can actually get a tour inside?
I hope so. Yeah.
That would be fun.
Absolutely. Maybe even get the telescope out. Yeah.
Yeah. Because when I went, when did I see you? Was that August? I think it was August.
Yeah, we were
everything
not allowed
was
anywhere near the observatory. Yeah, it was like, yeah.
Yep.
Well, if you guys ever come to LA, you let me know if you're going to be here this next year sometime, because the template membranes I mentioned before, we've got them set up, deployed, and there's an observation room I could take you in and show you. So you let me know if you're in the area.
Also, Redondo Beach.
Yes.
In Redondo Beach, California. Yep.
I have been in the parking lot there, but I've not been inside.
Oh, well, you got to make a trip. Come out this year.
I didn't have the contacts last time I came, so
now you have a friend. Well, I might be in LA soon because I'm putting together or at least I think I'm putting together a really, really exciting elite interview with someone really big. So hopefully, yeah, I don't want to say who it is because I don't want to but if I'm there, I will
If you
come.
have like if you got like an hour you can spare, you let me know.
Easily.
Meet up at Redondo Beach. Okay.
Yes.
Cool.
And I mean, TRW, as I still call it,
Before,
is, has, I want to just say, it has such a history in the space industry. We've been focusing on James Webb as its biggest and latest science project, but TRW has been in the space program since the 1950s with the Thor Able missions, with the first Pioneer lunar probes in the 1950s, with the solar pioneers, including Pioneer 6, which was launched in 1965 and worked for like 30, 40 years. And more recently, of course, it built Chandra,
that's right.
which I work on. And so
and some of the people I worked with on Webb worked on Chandra. So
right, and we are still operating Chandra, and just thanking TRW Northrop Grumman for the fabulous job they did on that spacecraft. It's just outstanding. So when you visit Northrop Grumman, don't just think Webb, think a whole history of really important missions, plus some ones that he's not allowed to talk about today. Yeah. But that's a whole other subject. Yeah,
definitely. Well, hopefully soon, hopefully within the next couple months. So
awesome.
I'll let you guys know, but thank you so much for joining the chat. Thank you to all of the people who have commented and participated. And I guess that's it.
All right. Well, lovely to see you, Ellie. Great to meet you, Jeff. Let's stay in touch.
Yes. Great meeting you too, Jonathan. Ellie, thank you for setting this up. This was awesome.
Of course.
Sorry for my internet. I'll get it fixed.
It's all right. You got to get Starlink, I guess.
I guess so. I'll go look into it.